All right, so for page 80, label it exponential functions properties. A definition of an exponential function is that is of the form f of x equals a to the x. A in this case would actually be some number. It can't be 1 and it has to be positive. And x is going to be the variable, and so the exponent will now be in the variable. Typically we normally have the variable as x as the base, and then the exponent is like a 2 or a 3. But we're going to reverse that now, and so this turns us into an exponential function versus a polynomial. All right, so these are some properties that we're going to go through in just a minute. So your foldable will look like this. Each of these will be folded on the vertical lines here, but then they'll be cut along these horizontal lines here so that you end up having 6 tabs altogether, and you'll be able to open every single one of these tabs with the different things. So the first thing we're going to talk about is the base, then we'll talk about the exponent, the y-intercept, the asymptote, the domain, and the range, and the end behavior as well. Okay? So when you open these up, if you open up base first, we said that this had to be a constant. The base is typically used as the letter A, so it's going to be some number that's going to be positive, but it cannot be equal to 1. The reason it can't be equal to 1 is that when you take the number 1 and you set it to an exponent of x, 1 to the x power is just still 1, which means you would just have a horizontal line, and so it wouldn't be exponential anymore. The exponent is going to be your variable x, and then down here we have your y-intercept. So that means when you plug in x equals 0, you would have y equal to a to the 0. A to the 0 is just simply 1. So your y-intercept then is going to be 0, 1. That's if you don't vertically stretch it, move it up, down, left, right, and so forth though. That's just if it's just your parent function, a to the x. So it has a y-intercept of 0, 1. Your asymptote, we'll see in just a little while, is going to be the x-axis. It's going to be at y equals 0. Your domain, we'll see in a little while, will be all real numbers. The reason for that is that no matter what x is, you will always be able to plug in a value there, no matter how big or how small. And so you can plug in whatever you want, so the domain is all real numbers. However, when you're looking at both of these, your range, you'll notice, stays above the x-axis, so therefore y is bigger than 0. It doesn't touch that horizontal asymptote, so therefore we can't put equal to 0 on there for your range. And again, this is if you don't move it up, down, or reflect it or anything like that. This is just for the parent function. And for your end behavior, looking at these two particular graphs, you'll notice that when the when the function is increasing, as x approaches infinity, y also approaches infinity and gets bigger and bigger. However, when x goes in the left direction and approaches negative infinity, y is actually getting closer and closer to that horizontal asymptote. Y is approaching 0. Same thing is happening with your decreasing. But in the opposite order. So when it's decreasing, you'll notice what had happened for this one is that it is approaching the horizontal asymptote as x gets closer and closer to infinity. So as x approaches infinity, y approaches 0. And then if you're looking at it to the left instead, as x goes to negative infinity, you'll notice that y is approaching infinity. So let's look at a couple of examples here. You're going to do these two examples as well on yours. So we have y equals 2 to the x here. And so I made a table, x, y, and then I plugged in some numbers. Since the domain can be whatever I want, I chose -2, -1, 0, 1, and 2. So if I do 2 to the -2 power, remember that's the same thing as using its reciprocal, 1 over 2 to the +2 power. 2 squared is 4, so -2x is going to give me a y of 1/4. When you plug in -1, we'll have 2 to the -1, but that's really the same thing as 1 over 2 to the +1, so that's 1/2. When you plug in 0, you get 1. When you plug in 1, you get 2. When you plug in 2, you get 4. So I plotted these 5 points here. I've connected the dots, and I have here a horizontal asymptote as y equals 0. This is showing you exponential growth. And the reason we know that is because this is an increasing function, and this is going to be true when your base is bigger than 1. The second example we're going to do is just simply 1/2 to the x instead. We're going to use the same domain values, -2, -1, 0, 1, and 2. When you plug these in, 1/2 to the -2, remember we use the reciprocal instead, so that'll be 1/2 to the -2 is the same thing as using the reciprocal of 1 over 1/2 to the positive 2. That's going to be the 1/4, but then you have 1 over 1/4, which is going to turn that into 4. Same thing will happen with -1. You'll use the reciprocal, so you have 1 over 1/2, which when you multiply by the reciprocal, becomes 2. Plug in 0, you get 1. Plug in 1, you get 1/2. Plug in 2, you get 1/4. As I plotted these, you'll notice that the dots are actually starting to go down this time. So as I connect these dots, I'm going to put my arrows on there. We've got a shape that is an exponential that is decreasing this time. We call this exponential decay. And this is true for any values of a that are between 0 and 1. So any fractional form in here between 0 and 1, you're going to have exponential decay instead of growth. And that is it for this page.